I will be talking about effects handlers and Bicomodules, and this is joint with Owen. And so to start off, like everyone kind of knows the story of category theory and CS as like programming languages. And there you have these functional programming languages, and you have a category whose objects are the data types and whose morphisms are the functions. And then the way that this actually became useful enough to work is that Maji introduced monads that would handle effects. But the problem, I think, or a problem maybe, is that or what I've heard, is that when you have real programs, you just have effects after effects after effects, and you have a bunch of monads. And when you compose these long stacks of monads, it actually becomes very unwieldy. And so another point of view could be that we should be putting effects more at the forefront. And I don't know where the right line is, but in this talk, I'll be talking about, so Owen wrote a blog post recently about this very subject, effect handlers, and they're just putting effects at the forefront. And so he called it imperative programming using polynomial functors or something of that sort. Which is a draft. It's coming out soon. So poly, today we'll be talking about poly as usual for me, and poly is in CS. Comes up in all sorts of places. It comes up as databases because databases can be understood as categories and co-presheaves on them, and those are polynomial comonads and bicomodules or coalgebras. Databases, dependent type theory. So this is work of Steve Audi and others. Algebraic data types. So algebraic data types are exactly polynomial functors, and they're free monads or free algebras. Lenses are polynomials or maps of polynomials that are between monomial. So maps of monomials are called lenses. Finite state automata. These are Moore machines, or regular languages are equivalent to finite state automata and stuff like that. These are polynomial coalgebras also. And with Chris, we're working on some rewriting protocol stuff that'll be using polynomial functors. So polynomials come up all over the place in CS, and maybe there's some way to link all these different things. But today we'll be kind of linking this one, not really databases, but Bicomodules, which are the duck queries or different uses of conjunctive queries that connect one schema to another. Finite state automata kind of, and yeah. And so, okay. And we'll be doing, I guess, imperative programming. With effect handlers. So I'm underlining the ones that are kind of relevant today. Okay. So the way this started is Owen was looking at these effect handlers, or a programming language maybe you were even inventing or finding. You're here's what I wish they kind of felt like. And then noticed that they looked polynomial and wrote down these maps of polynomials, and I was like, oh, that looks like this, maybe it's one of these, and he wrote down long formulas, and I oh, that's that, and that's that, and I would kind of make it smaller and smaller, and then it just became this form that we found today. So, but it was amazing is that this form actually works really well. So I feel like you hit the nail on the head, and so that was great. So the plan.
Well, that was after about a week of is it this? And it
yeah.
was no,
yeah, we iterated back and forth. I was I don't like that.
No,
yeah.
I don't like that.
But eventually it just worked really well. So the plan is first to talk about left-con extensions in poly. So poly has all sorts of structures, but one is that it has left-con extensions. Two, something I call selection categories, which I just thought were a weird way of constructing new categories from old, but it turned out that they're very relevant for this story. And then three, effect handlers. How they work. Okay, so to begin, Poly is the category of, so an object in Poly is a coproduct of representables. Coproduct of representable functors, set to set. So you could write it as the sum over some indexing set, which I'm calling P of 1, of y to some power. Maybe this is not. So this is a polynomial. And the reason it's called P of 1 is because if you plug P1 into this thing, you get, this turns into just 1, and you get that. So it's kind of like this indexing set turns out to be P of 1. And you can compose polynomial functors. If you take the composite of two polynomial functors, you get a polynomial functor. And so you get this monoidal structure, poly, whose unit is y, the identity functor, and whose composite, I didn't know with this thing. So P triangle Q means plug Q into P. This is P of Q as functors. The reason I write them this way is because I don't like to think of these as functors. Even though they are functors, and the morphisms are the natural transformations, they really, in all of these cases, act more like, or many of these cases, act more like just data, like object, like these functors are the objects of a category, not the morphisms. So I don't want to write compose, and they feel more like data structures than functors. Okay, but you can consider them as functors from set to set. P. So P will take a set and coproduct together lots of powers of that set. So the left Kohn extension of P along Q turns out to be polynomial. So the initial thing here that receives a map like that is polynomial. And so, in other words, polymaps. Now, in every case of Kohn extensions that I think is useful, they are pointwise Kohn extensions. So for me, a Kohn extension really ought to be the sort of thing that's an adjoint here. What that means is polymaps from P to R of Q is polymaps from something, from this left Kohn extension along Q of P to R. A pointwise Kohn extension means that composing with this is right adjoint to this machine here. Left Kohn extension is a left adjoint to composing with Q. So this LQ thing is the universal thing that maps to R. This LQ thing is the universal thing for which there's a map from P to Q composed of it. And I have been writing this PQ. That's just notation I've been using because this is like Lenzy notation, and because when you write out certain things with poly boxes, if you've ever heard of those weird things, it kind of feels like you're taking P and putting Q on top. But whatever it is, this thing is a polynomial, and I can tell you its form. But we could also just prove it. So LQ is a left adjoint. It's the left Kohn extension. Therefore, it preserves coproducts. So I know that LQ of P is the sum over all I in P of 1 of LQ of y to some power. Because it's a left Kohn, because it preserves coproducts, preserves all colimits. So what is LQ of y to the pi? Okay, so polymaps from y to the pi. Let's just rename this thing. Let's just say we had a single one of these. A is a set. I'm writing this out. It says R compose Q is polymaps from LQ, which is what I want to know, of y to the A to R. So, but this one, by the Oneida lemma, is R of Q of A. And this one, I just set LQ of y to the A to be y to the Q of A. Because if I made this thing y to the Q of A, then by the Onet lemma again, I would get R of Q of A here and here. So the point is that LQ of P, which I usually denote PQ, is the sum over the same thing that P is a sum over of y to the Q of P bracket I. And that's the left Kahn extension in poly. This is the initial polynomial that receives this map, and it's the initial functor that receives this map. The initial functor happens to be polynomial. Okay, so that's left Kahn extensions. And that is, I might be going super fast, I don't know, but we're done with this one. So now we're ready to say, oh, by the way, I want to say that Josh Myers is the one who showed me that this exists. Said, oh, this exists. And then Todd Trimble is the one who reminded me that that polynomials are functors and that therefore this is actually a left Kahn extension. I was just thinking of it as I was just calling it co-closure decomposition. So I was just writing PQ and then saying that this was a co-closure. Okay, so part 2 or so. 1. Okay, part 2, selection categories. So the day that Josh said, oh, this exists, the first thing David Jas Myers said is that, oh, then for any polynomial PP, this is a comonad for this structure, for the one we've been talking about. So I guess you can always do that. Whenever you have like a closure or a co-closure or something, you'll always find a comonad or a monad by putting the same thing twice. So that's great, but I knew at that time, because of, I guess, Amin and Ustalu, that comonoids in poly are categories. So I was like, oh, well, then that thing's a category. What category is it? Yeah, it turns out, i.e. a category. And what category is it? It's the category whose objects, let's just call it C, I guess. Ob C is like P of 1, and Hom from like one object in P of 1 to another object in P of 1 is the maps in set op from P bracket I to P bracket I prime. In other words, a full subcategory of set op. So for example, if we used P list, by which I mean the polynomial over all natural numbers y to that natural number, you plug in a set A to this and you'll get 1 plus A squared plus A cubed. In other words, lists of A's. That's why I called it list. Then list is fin set op. And so these will be selection categories, but selection categories are more general, because if you look at that, you wouldn't know why anyone would call that, where the word selection would come from. I realized a little later that that for any comonoid, you can do something. So for any category C, so a comonoid in poly is the same thing as a category. They have different morphisms, but they have the same objects. And for any polynomial, it turns out that and P in poly. P compose CP is a comonad. be a category. So what category is it? Okay, here's what category it is. So I'll just give it to you by examples, I think. I mean, I could try to write out with the. I'll just give it to you by example. Why did this thing is a category. Its objects are ob c to the a. So basically, you have a bunch of objects in C. An homomorphism would be another 5 objects in C. And for each one of them, you pick one of these and you give a map. You give some kind of map. Sorry, you give a map in C. So for this one, we pick an object, okay. For this one, we pick an object. For this one, we pick an object. For this one, we pick an object. And that's a map. For each one of these, you pick something to pull from, and then you give a map in C for that form. So like, if we did it again, how do you compose? Okay. So the composite of these is pretty easy. It would be this guy pulls from there. This guy also pulls from there. This guy pulls from also there. And this one goes from the top one. And this one goes from there.
So is this living inside the free product completion C? Is that
Well, this is C to the A.
like, yeah. But are these maps the same ones that are in the?
Oh, yeah.
You look backwards.
Yeah.
From the
Yeah, this is the free prod. These are in the free product completion of A. So I feel like if I did list here, right?
Because it's a read product.
It's
You can map.
so we're saying we're hearing a wreath product.
You can use gamma.
Is this what is it? Wreath product? Is a wreath product this with list?
The read product is more general, at least in my.
More general than selection categories?
Yeah, because any of these is a read product, and if you replace Y via with list, you get the free product completion.
Yeah, interesting.
This one lives inside that very.
Cool. So the reason I called these selection categories was just because it felt like this guy had some pretty good reproductive success, and this guy was okay, and then these guys kind of died out. And the reproduction is not that you actually are copied, but you are updated according to C. You're allowed to move forward along C, but you're right. I think product completion is thinking of this as something like a subcategory of the free product completion seems good. Okay, so this is Y to the A compose C. What else did I consider? Yeah. So you could see that if A was 1, then you wouldn't have 5 copies, you'd have 1 copy, and you would just literally get, why am I saying that? Sorry, you would get C. That's not what I meant to say. If C was 1, if C was the 1 object category, then you wouldn't have any labels here, and you would just get fin set op. Sorry, one last time. I've already said that list is fin set op, but now you can see it again. The idea is that an object here, in general, an object, maybe I should just say what an object is. An object is some position in P, and for every direction in P, an object in C. And so if C was 1, the 1 object category, then you would just get and P was list, you would just get as an object a finite set. And as a morphism, each one of these guys would choose one of the others to come from, which is a map of finite sets off. Now, when I made these things, when I was writing about these things, I was like, huh, it's pretty interesting when I have like y to the a plus y to the b as my polynomial. Or things like that, where b and c are different. Because what this will be is things like, you have either a many things or b many things. Maybe a is 5 and b is 3. And you're allowed to kind of do these selection-y things. You know, go from 3 to 5 and then 5 back to 3 and do whatever you want. But I thought it wasn't that interesting, or I didn't know the point when you had like I wouldn't have guessed that this would be interesting. Because what this is it's an object in it is a pair of an element of A and an object in C. And then a morphism, so you just pick some object in A, element of the set A, pick some C, and a morphism is like a map in C and just like a brand new A. So a morphism is just there's no relationship between the two A's and it's just a map in C. So I didn't think this was very interesting. But in the selection, it turns out that these are interesting because these A's can label state in your effects handler. And that's what we'll see in a minute.
What's the category AY over AY?
It is it is the, what's that called? The co-discrete, like the groupoid on A. That makes sense? So it would just be like the objects are the objects of A, and there's a morphism between any two, a unique morphism between any two. So it's quite boring in some sense, but
You still get this read
yeah. So I think I'm going to be, I didn't run this talk, so I think I'm going to be fast. It is. So for example, yeah. So what is SS? SS is SY to the S. So yeah, not sure why I'm saying this. These come up a lot in like dynamical systems or more machines and things like that.
SS or SY?
And SY, both of them. The full subcategory of set spanned by the object empty set, and that spanned by the object 1 look very similar. This is S many copies of the empty set and all the maps between empty set. And this one for SY is S many copies of the one element set and the maps between one element sets. Okay, so for effects handlers, I'll give you some math. So first of all, math thing number 1, the following are equivalent. So we have a polynomial P. It's all math?
No, the paper that you started writing, like everything that you write in poly seems to just be like a bunch of the following are equivalents.
I do like those. So yeah, M and poly, C and D are categories. In other words, they're polynomial comonads. 4. So given these things, the following are equivalent. 1, maps phi. So this thing will be called the effect handler. C composed M. So if I had one of these, I want it to satisfy 2 properties. So let's think, we call this thing phi, and it goes from MD to CM. And C and D are both comonoids. So a comonoid has 2 maps. It has a map like that, and it has a map like this. A duplication and a deletion. And so I want this phi to satisfying M D run phi kill off C should equal, this is M, and this is D MD. So killing off C should be the same as just running M.
So can you interpret C, D, and M for us in the context of a stateful computation?
So, yeah. Let me go to number 2.
Okay.
Let me go to number 2, and then I'll do
You're
it.
about to do that.
Well, yeah. Sure I was. I think I would have. The other one is that MD, run it through phi, and then duplicate should be the same thing as duplicating, running this one through. Note that's M, and that's D, M, D, C, and then running that again. C, M. So hopefully these pictures are like kind of nice. Like you can write this you could write this as, sometimes I might want to write it like that, and then these would look like, but this is not a distributive law, which I often also write that way, but one of these would say this, and the other would say this. Okay, so that's condition 1, that's the first thing. That would be called an effect handler. Another thing that you could call an effect handler would be a map from the selection category. A cofunctor. A cofunctor just means a map of comonoids. So this is a comonoid, I told you that before. C is a comonoid, and this is a map of comonoids. So it sends objects to objects, and then morphisms in C backwards to morphisms in this other thing. And so this is the thing that I think that Owen originally wrote down, close. He wrote it for not comonoids, but just polynomials. But here's what it's saying. M is giving you state upstairs, like some element of M. You've got a state labeling. You got a state label, and then you've got a bunch of objects in D. From that data, you can get an object in C. It's like, oh, I can summarize. I've got all these like pointers, or I don't know what to think of them as. I've got all these like, I'm watching all these machines. Machine 1, 2, 3, 4, and 5, and I'm in state M. Phi then summarizes that as an object in C. Then, given a morphism in C, someone asks you, hey, can you update like this? That causes a new state, and all of the registers or pointers or whatever we should think of these as, to pull from the old state and update them. Owen, do you want to say anything that I can?
Yeah, maybe one way of thinking about it is that
I will give it a Turing machine example from Owen's blog post in a few minutes, but yeah.
Well, one thing that you might want to say is that, like, a machine here is a coalgebra for D.
Yeah.
Alternatively, if you think about D as a category, it's a Copri sheaf on D.
Yeah.
And basically, it's a set of states along with a function from like the set of states S to D of S. So each state has a position in D, and then at the position you can update according to like the morphisms going out of that position.
And what is D itself? What is it?
It's an arbitrary category, but we will see it as, yeah.
Yeah, we'll see some examples. But
Yeah.
you can think of like an object in D as sort of like the external state of this machine. And so this forwards map allows us to translate like a bunch of external states of D machines into an external state of a C machine, and then a transition of the C machine back into a bunch of transitions
Yeah.
of the dimensions.
Yeah, so you've got these, yeah, you've got this handler M. I'm not sure whether to think of M. M is kind of like this material substrate, and then phi is like how the handling happens. So M is like, oh, I've got a bunch of things I'm watching. Each of them is an object in D. And now this thing summarizes that to like some end user C. The end user sees something on their screen or on their REPL, they write a command. That command gets sent back to a new state of M, and for each of the registers or whatever, it pulls information from a previously held register. Okay, and then 3, a Bicomodule. Well, maybe I should do more than 3 so that you can know what a Bicomodule is if you don't already, of the form C, D, M compose D, of the form. When I say this, it's slightly lying. What I'm really saying is that a Bicomodule, if you have a C and a D, and these are categories, but you can think of these as comonoids in poly, then what is this? This just means, this is a syntactic sugar for a map from P to C compose P, and a map from P to P compose D, satisfying a couple rules. And so in this case, I'm asking that the map from M compose D, that's P, I'm asking that this map, I'm implicitly asking that the map from this to M compose D, which is required there, be the diagonal, the codiagonal that D as a comonoid has. So that's implicit in this thing. So a Bicomodule, I guess, one way to say this is that it's a parametric right adjoint. Maybe you don't know what that is either. It's a bunch of duck queries, if you know what that is, from D set to C set. So what that means is that we're getting a way of taking D sets to C sets where every C set has like a disjoint union of conjunctive queries as a way of getting its on D set as a way of getting that C set. Okay, so these are equivalent. And great, so that's math thing number 1. Math thing number 2 is that every Bicomodule of the form C0 and CY arises in this way. And these are more, this one's more, I think, even though it's less information, it's more interesting because these are exactly the co-presheaves on C. A co-presheaf on C and a Bicomodule to 0 are the same thing. Both in and a C coalgebra, if you think of C as a comonoid. So if you think of C as a category, these are the co-presheaves. If you think of C as a comonoid, these are either the Bicomodules to 0 or the coalgebras on that comonoid.
And composition.
Okay, that's the next thing. Yeah. And the next thing is that C, if you have one of these, M compose D, in other words, something that's equivalent to that information there, and you have N composed E here, that composite is M composed N composed E. In other words, if you had one of these and you also had N composed E mapping to this thing, oops, no, to this thing, then you could compose them and get like an N composed E thing mapping to a C composed M thing somehow. Why am I confused now? Well, somehow this is true. No, N. Then I can get an, maybe I did it backwards with respect to that one, N composed M composed D thing. Should I write that out?
I think it's nice,
Yeah, right, nice to write out, okay. So if I had,
On the other board.
yeah, maybe here, or is it, can you see that?
yeah.
The thing can see everything. Okay, so if I had M composed D to C composed M. And then I had N composed E to D. I shouldn't do this because I might be right. How do you do this? What? Maybe I'm being really dumb to try this.
Start with the M composed N composed.
Then I M composed N composed E
And then we
maps to M composed D composed M.
Compose
Which-
N.
N.
There's N on the line.
Oh, there we go. Okay.
and then
Which maps to C composed M composed E, which is the required form.
composed N.
C composed, sorry,
C composed M composed N.
N. Great, yep. Cool. And the point is that that is the bicomodule you get there. So why is that interesting? Because what that means is that that these form a full, well, these form a two full sub double category of cat sharp. So, well, like same two cells. So I guess like effects handlers is a subcategory of cat sharp. And so its objects are comonoids, the same as before. The verticals are cofunctors, same as before. But you could require these to be effects handlers. And everything will be good, and they'll compose correctly, et cetera. And just take the same two cells. And this thing has conjugates, in case you care about that sort of thing. The reason is because when you take M to be Y, the identity, this thing just becomes a cofunctor. Like the rule for this, when you look at what these two rules say, this will just be a cofunctor from D to C. So every cofunctor counts as an effect handler. Okay, so that's the thing. Yeah. Okay, so then we're trying to get to something that it all feels computer science-y. So elementary effects handlers. These are what Owen actually wrote down. So if C happens to be the co-free comonoid on some P, then it's just a fact that a cofunctor from anything, from any comonoid to C, is the same thing as just a regular old map from the polynomial to P. So that's thing one. I can reduce when C is co-free, I can reduce this definition a bit. I don't need a cofunctor, I just need a map of polynomials. And then if D is the co-free on some Q, then then there's a map from D to Q. And so if I had M composed Q to C composed M, then I could precompose that with D composed Q, M composed D, sorry. I could use this projection and get all the way like this. So I'd be able to get one of these guys from just this data. So,
And you can make that C a P.
and then I can make that C a P from this thing. So now to finally, an elementary effect handler from P to Q. This one, I guess, would be an effect handler from C to D. Is M in poly, I guess we'll define it. M in poly and a map from M composed Q to, why did I do it that way? From Q to P, I guess I should say. P composed M. So in other words, from one of these, should I say this out? Maybe I should. So from one of these, M composed Q to P composed M, that gives me a M composed co-free on P, on Q, to P composed M, using this trick. And then that's the same thing as a map from M composed the co-free comonad on Q with M. That's that selection category thing to P. And that's the same thing as a cofunctor, which is the old version of what an effect handler is.
We might say a classical.
The classical effects handler. Okay, so finally we can like say what this is. Or let's see. So what is this thing going to do? What is this? This thing is apparently related to effects handling as like imperative programming, according to Owen, at least.
According to my blog post.
According to the blog post. Okay, so what is that? Yeah. Remember before we had like these selection categories, we had like a bunch of M, we had like a label of M, and then we had all these dots, which was like the directions there. And for each of them, we had an object in some category. Now that object is like the state of a Q machine, like a machine that outputs positions in Q and inputs directions in Q and updates its state. So those are what are here. These are machines that are outputting some value and waiting for input. And then, given one of those, you can summarize it as a single position in P. And if you had a machine running P, then whenever you give it an input, it can somehow kind of shuttle things around and give that an input on Q and update its state. So I don't know if I said that very well, but it's a much simpler sort of thing than like the big one that I just erased. It's a kind of one step at a time machine that's simulating, like you've got this M and it's simulating it. It's showing the user P-ish stuff, having the user input P-ish stuff, and in the background it's running like a bunch of Q machines, keeping state and like updating them one step at a time also. So let me give you the Turing machine example that Owen wrote in his blog post, which was a very simple case of this. So here M is 0, 1 to the Z times an element of Z. So this is so M is going to be kind of the substrate. Here's the tape. So the tape is a bunch of zeros and ones and a position. And Q.
That times Y.
Oh, sorry. Y. Meaning we're going to hold this as state. That's going to be that that's that thing. And then instead of having lots of dots, this thing is just running one Turing machine. One dot. That's why there's a 1 here. Q, the thing that is in the background running that the user doesn't see, is a complicated thing. It's the thing you think of when you think of a Turing machine. It outputs go left, go right, print 0, print 1, and it inputs either a 0 or 1 to write. And P is something that just says, like, I'm working here, working. It can output the word working and then receive just like unit input. Or, and I'm going to do something slightly different, it can output the entire tape. Because when the Turing machine is done, it outputs the entire tape. Do you have a question?
Well,
I don't. In Owen's
step
Turing
up and let's see if it works.
in Owen's Turing machine, In Owen's Turing machine, he just wants it to output either 0 or 1 at the very end. But in the notion of Turing machine that I think of as the usual one, once it's all done and halted, was there a +1 somewhere? +1.
In Q.
In
Q
Q,
should
yeah.
Because that's
Sorry.
the pulse.
Yeah. Okay. These lines were just to separate the Q and P. Okay. And so the user is just going to see something that's like working for a long time, and then boom, it just spits out its entire tape. Or you could have it spit out 0 or 1, like something was accepted or not. And so what we're saying is that the way Turing machines work is encoded by this data. Like, do I have time to write this down? And why would you care? Because if we had, maybe I should have said this, but here there's a theorem that says co-free Q set functors from this thing. This is a category. Functors from it to set are the same thing as Q coalgebras. And so what we found over here was like, or somewhere, was like we are able, from one of these things, if I could tell you one of these, then I would also be telling you a way to take CP, the co-free on Q to co-free on P. Which means I'm giving you a way to take Q coalgebras to P coalgebras. Sorry, I won't do that because they're like parametric right adjoint ways to do that. Okay, so in other words, if I can give you one of these, which I'm saying is how Turing machines work, then I will be giving you a way to take Q algebras to P coalgebras. What is a Q coalgebra? It's a set of states, and for every state, it outputs either halt or go left or go right, and right a 0, right a 1. And then it listens for what's on the tape. It listens for a 0 or 1 and then updates its state. So that's a Turing machine. So this thing equals Turing machines.
Well,
Turing machine data.
Turing machines are classically like,
Turing machine.
They're sort of confused.
Yeah, this
It's
is
like
the data.
It's like the finite state machine inside of a Turing machine.
Yeah, it's a thing it's a program, Turing machine program.
Yeah.
Turing program. And from a Turing program, we get a coalgebra on P, which means a set of states, and for every state, it just like, we don't know what's going on. It just says working. And then finally, we get a state that ends up in like a whole tape being produced. So, so a way to show the user just something that's like sitting there, a black box, sitting there, working, and then finally outputting its tape, can be obtained from a program. And the way it's obtained is by taking this tape as an effects handler. So it's like this imperative version of things, and that's why Owen called this imperative programming with poly or something like that.
Yeah, the idea is that like the positions in Q are commands that mutate the state of M, and also result in additional commands in P.
So M composed something. M is a linear polynomial. It's something times y. And so when you compose it with something, you just plug in that thing for y. I mean, in general, you always plug it in for y. But there's no power here. It's just, so I'm just taking this thing times Q. I don't know if I'm going to be able to write this out. Times 0, 1. Y to 0, 1. Plus 1. 2. I don't know if I'm going to want to write. Z composed M. So working, I compose it with M. That means I plug M in for Y. Working times 0, 1 to the Z times Z time plus 1. No, plus. What happened? 0, 1 to the Z. Working plus 1 times that. don't know whether I should go over this or not. Working plus 1 times that thing. Okay, so I guess I'll try. So if we had a tape position, and we have all this data, where's the y? Working y. Y plus 1. Does that look right? Okay, so we have all this data, and we have this. We have the tape. If we're in the halt position, go to the halt position and output the entire tape. So if you're in this summand there, go to the one summand and output the entire tape. The other cases, you're in this summand, you have a tape position, you have a tape and its position, and you have go left, go right, and output is 0 or 1, and you're going to end up in this, you're going to end up in this, and then the new thing you get here, this new tape position, is whatever happens when you kind of apply what it said to do. And then there's going to be a direction going back, and the direction you give back is like what you just read in from here.
Yeah,
No.
so critically, the order of things is
what you
write,
yeah.
then you move, then you read, and then you sort of
Yeah. Right, so the thing you put here on the directions back is whatever is currently at the read head of the tape.
Yeah.
In other words, this function applied to that. So all I mean,
after you move.
well, that is what happens when you have a
Yeah,
polynomial
yeah.
map, yeah. So, oh, right, yeah. So the point is, if you understood polynomial functors well and their maps, you would be able to say what you needed to write this map down. And as you wrote it down, there would be only one thing that seemed reasonable to write down. And what it would be is, you take your tape, you take your command, or your halt command. If you're in the halt command, just print out what's on the tape. If you're in a go place, you go, and then you update your tape according to the command that was here. And you read into Q what is at the read head of the tape. And so what that is it just how Turing machines are supposed to work. That's what's being encoded in this map. And given that, it gives you a way to like turn Turing machine data into a program that just runs for a while and outputs the thing. And in general, that's what these always do, but you can have like multiple cores or whatever running at once, and that sort of thing. So that's it.
Questions?
Yes.
So you said at the beginning that one of the motivating things here is how in programming with effects that you often have a bunch of them stacked on top of each other, and that we want to make these primitive to address them.
Yeah.
What would that look like?
I think what that would look like is operations on effects handlers. I don't remember many of them. One is that you can compose, so you can stack them that way. But it might also be the case, I probably shouldn't say anything, but there may be like monoidal products between these. Like if you have an effects handler from C to D, an effects handler from C prime to D prime, maybe you can tensor. In other words,
Yeah,
product the category. We did that? Yeah, okay. So you can tensor, so you can stack them vertically and horizontally. Maybe there are other operations too,
You
but
can also do co-product.
oh yeah, you can also do coproduct. These also work, by the way, so I was talking about polynomials here, but these work when, these kind of work, right, so I said C was a comonad, but C in fact could be a comonad like a cofunctor over something. It could be more like a comonad in cat sharp, not just in cat. And this whole, and like M could be, all this is like not just over in poly, but in cat sharp. I just don't want to, it's a much bigger story. But, and what that allows you to do is when you have that M with all these things there, you can kind of classify the different parts of, like the different cores you're running or whatever into different segments that update in a controlled way.
Do you or either of you know how these compare to monad transformers?
I do not know how these compare to monad transformers.
My understanding of monad transformers
monad transformers are about putting more, allowing yourself to do more effects. So it's like you have a monad, like you might have one monad and then you compose it with another monad and then you can do more effects. Whereas this is about like taking your monad stack and then like interpreting some of the effects and like reducing your number of effects potentially. Cool. So it's like, yeah, handling the effects. Right. So classically effects handlers are often of the form like Q equals
Yeah.
equals, forgot to hit shift. Or I hit shift. Q plus R. And so it's like, you interpret the things in R, and then you just get left with Q. And like, one of the reasons why people like effects handlers a lot is because plus is commutative. So it's like you can sort of, with monad transformers, monad's composition is very much not commutative. It's like you build this whole chain up and then you have to unwrap it in a very specific way. But for there, it's like, yeah.
Why do we think they have to be